Welcome back to another lesson. Today, we will continue our discussion of integrals, using them to make more advanced area and volume calculations. First, let's discuss how to find the area bounded by two curves. If we wish to find the area in between functions f and g, then we can integrate their positive difference over the length of the interval. To find the yellow shaded area, we would integrate f minus g from a to b. What we see in this calculation is a difference between an upper function and a lower function. We will follow this idea to complete practice question 58. Let's start this question by sketching the given curves in the xy plane. The line y equals x plus 1 forms the lower boundary of the region, and the exponential y equals e to the x plus 3 lies above it, working its way up and to the right in the coordinate plane. The vertical lines x equals 2 and x equals 4 form the left and right-hand bounds of the region. Our job is to find the area of this region, which we are now shading in yellow. Since there is only one upper and lower function over the horizontal length of the interval, we can find this area with a single, definite integral. We will just need to integrate, from 2 to 4, the upper function minus the lower function. The integrand simplifies to e to the x minus x plus 2, which we can integrate by taking antiderivatives. The antiderivative is e to the x minus x squared over 2 plus 2x. Plug in the upper and lower bounds into this rule to then perform an upper minus lower calculation. The result is e to the fourth minus e squared minus 2, which is the area of the shaded region. Question 61 is similar to our last problem. Take the time now to sketch the given information in the xy plane. Pause the video and try to find the exact area of the stated region. Then circle back to check your work and see how you did. The answer is pi minus 1. If you got this expression, then you have correctly found the area between two curves in the coordinate plane. Investigation 24. How would you find the area that is enclosed by the given curves? An integration with respect to x wouldn't work well in this situation, and here's why. Let's label the leftmost and rightmost ends of this region. When we integrate with respect to x, we should look for consistent upper and lower boundaries. The problem that we run into here is that the lower boundary is not a consistent function. The lower boundary at the start of the interval appears to come from the parabola, and later this changes, where the lower boundary appears to come from the line. To integrate with respect to the x variable, we would have to use two separate integrals. The first integral would be for this leftmost part of the region in pink, which only uses the parabola and not the line. The next region has an upper bound formed by the parabola and a lower bound formed by the line. While we can use two separate integrals to solve this problem, it seems quite challenging. Fortunately, there is a better method. A better option is to integrate the region with respect to the y variable. We can see that the region has a consistent rightmost boundary with the line and a consistent leftmost boundary with the parabola. And this is true for all values of y within the region, from the lowest y value of -2 to the highest y value of 6. Consequently, we can find the shaded area with only one integral, which should take us through these two values of y. Integration with respect to y leads to rectangles with a vertical base of dy and a horizontal length that is the distance between the right and left sides. We will want to solve each equation for x so that we have a way to find these lengths at any value of y. The setup of the integral should show that we are subtracting the rightmost function from the leftmost function. The correct integral is the integral from -2 to 6 of y minus y squared over 4 plus 3 dy. The value of this integral is 64 over 3, and we got there through an integration with respect to the y variable. Next, let's talk about how to find the volume of a solid with known cross-sectional areas. Let's create a cylinder on the left and an irregular solid, with circular cross-sections on the right, on the interval a to b. The cylinder on the left will have circular cross-sections of constant area through the entire interval. The leftmost end of the cylinder has a circular base with an area that we'll call a of x. Integrating this area function over the length of the interval gives the volume of the cylinder. You should understand that the expression a of x times dx gives a volume calculation for a small piece of the solid, and the integration is the sum of all of these pieces within the interval. Being able to write the cross-sectional area as a function of x is more important in the case of an irregular solid. This is because the cross-sectional areas change over the course of the interval. If we look at different values of x and identify the cross-sections that take place, we can see that they have very different sizes. That is why we need to write a rule, or a function, that describes the area based on the x value. With each cross-sectional area comes a small change in x that creates a sliver of volume. The integral is a sum of these volumes, giving us the total volume of the irregular solid. In summary, to find the volume of a solid with known cross-sections, we will need to integrate the area function that describes these cross-sections over the length of the interval. Let's put this knowledge to the test with question 62. We first need to identify region R in the coordinate plane. Having this visual will make it easier to write a rule for the square, cross-sectional areas that lie perpendicular to the x-axis. Next, highlight the x-axis and draw a line in region R that is perpendicular to it. This should be a vertical line, and it represents a side of the square cross-section. To get a sense of the square, try to imagine a square popping out of the plane of the page, like it's coming out towards you. This square has an area, and this is one of the cross-sectional areas that will be encompassed in our integral. No matter where we look in region R, we could draw a square that pops out of the plane of the page. If we drew all of them, then we would have the shape of the three-dimensional solid that the problem is referencing. Luckily, we will not need to see all of them to find the volume of the solid. We just need to write one rule that describes the area of each square cross-section, and this rule should be written in terms of x, because the areas change with the x values. So, how can we write the area rule for these square cross-sections? From our diagram, we can see that the vertical line in the region represents a side length of the square. This side length amounts to the distance between the x-axis and the curve, which, in turn, is simply the y value of the curve, or 6 root x. If this is a side of the square, then what is the square's area? The area of any square can be found by squaring one of its sides. If we square the side length 6 root x, then we find an area function that is equal to 36x. It is this area function that we will want to integrate over the full length of the interval, from x equals 0 to x equals 4. The value of the integral is 288, and this is the volume of the solid. Many problems that involve solids of revolution can be answered using cross-sectional areas. A solid of revolution is formed when a region of space gets revolved, or rotated, about an axis. This rotation leads to circular cross-sections. To get a better sense of this, imagine rotating a singular point about an axis. The point would travel a complete circle as it moves around the axis of rotation. The distance between the point and axis of rotation is the radius of the circle. Furthermore, this circle has a particular area, and that area can be calculated using the area formula pi r squared. When we move on, to calculate the volumes of solids of revolution through the disk and washer methods, we will use this area formula. The disk method will be used when the axis of rotation doubles as a boundary for the region. In the diagram on the left, You can see that the axis of rotation forms the lower boundary of the region. The region highlighted in yellow gets revolved around the red line. As a result, the revolution creates a solid, with cross-sections that are complete circles or disks. To find the volume, we would just need to integrate the area formula that describes these cross-sections. In essence, we will integrate pi r squared over the length of the interval. The washer method will have to be used in cases where the revolved region is removed from the axis of rotation. In other words, there is a gap between the region and the axis of rotation. In our diagram to the right, we can see that the shaded yellow region does not touch the axis of rotation. Consequently, the rotation leads to a solid with cross-sections that look more like donuts, or washers, which have a missing hole in the middle of them. Each cross-section has an outer circle and an inner circle, and to find the area of this one cross-section, we will need to find the difference between the areas of these two circles. We will then be able to integrate this area difference over the length of the interval to find the volume of the solid. In summary, we will need to take the area of the larger outer circle and subtract out the area of the smaller inner circle, which is the missing part of the washer. By integrating this difference, we will get the volume of the solid. Let's try out question 67, which uses the disk method. Since this question contains a rotation about the y-axis, we will need to perform the integration with respect to the y variable. This is because the circular cross-sections that result from the rotation actually lie perpendicular to the y-axis. The radius of each circle is the distance between the y-axis and the curve y equals ln of x. To perform the integration with respect to y, we will need to solve this equation for the x variable. You should see from the diagram that the radius of each circle amounts to the x-coordinate along the curve, and this value of x equals e to the y. Next, the area of the circle is found by multiplying pi to the radius squared. It is this area rule that we will need to integrate over the length of the interval, which starts at y equals 1 and goes to y equals 3. The integral can be solved without a calculator. Take the antiderivative, perhaps with u substitution, then follow an upper minus lower calculation. The final answer is pi over 2 times e to the 6th minus e to the 2nd. Question 69 uses the washer method. We can see how the shaded region does not share a boundary with the axis of rotation. In this situation, map out the lengths from the axis of rotation to the outer and inner boundaries of the shaded region. The longer length is the radius of the larger circle, and the shorter length is the radius of the smaller circle. Write each radius length in terms of x so that we can perform an integration with respect to the x variable. By using these expressions for the outer and inner radii, we will be able to write and evaluate a definite integral that gives the volume of the solid. The integral is easily solvable by hand, only requiring the use of power rule. The final answer comes out to pi over 6. You have now used the washer method to find the volume of a solid of revolution. Sometimes, the volume of a solid of revolution isn't easily solvable using the disk or washer methods. The method of cylindrical shells gives us an alternative when this is the case. For example, what if we had to revolve the region bounded by this parabola and the line y equals 0 about the y-axis? The disk and washer methods will be difficult to implement. This is because the radius amounts to an x distance, but the equation of the parabola is not easily solvable for x. Consequently, we'll use the cylindrical shells method. This method uses a rectangle in the region that is parallel to the axis of rotation. This rectangle has a vertical height of y and horizontal base of dx. When this rectangle gets revolved around the y-axis, it creates a cylindrical shell. To find the volume of this cylindrical shell, first think of opening the shell so that it lies flat, like a sheet of paper. The open shell is actually in the shape of a rectangular prism. The height matches the height of the rectangle on the left. And the depth of the prism is equal to dx, a small change in x. But what about the length across the prism? This is the length around the circular ring of the shell, which would be the circle's circumference, or 2 pi r. In our case, the radius r amounts to the x variable, so the length is described as 2 pi x. We will use the fact that the volume of a prism is length times width times height as a basis for our integral. The integral from 0 to 2 of 2 pi x times 2x minus x squared dx gives the volume of the solid. Now let's put this knowledge to the test. Attempt question 71 on your own. Pause the video and circle back when you're ready to check your work. Did you use a height of 2x squared minus x cubed and a radius of 4 minus x in your integral setup? Did you use bounds of x equals 0 and x equals 2? If so, you should have found a volume of 112 pi over 15, which is the correct volume of the described solid. You have just completed Lesson 6, Integration for Area and Volume. Keep studying, and I'll see you in the next video.